This is section 5 for chapter 1 on mole calculations, which is basically called stoichiometry, or stoichin. We're going to break this into two videos, and because it's kind of a long section. So in stoichiometry you have a balanced equation. It's a recipe of starting ingredients and your finished product. In this case we have iron oxide plus carbon monoxide, and it yields iron solid and carbon dioxide. So in a balance the following equation, you have to balance everything first. You do an add and inventory. You should get 1 iron oxide, 3 carbon monoxide, 2 irons, and 3 carbon dioxides. Every element is balanced. 2 irons, 6 oxygens, and 3 carbons. So what do these coefficients tell you about the reaction? Basically you have ratio of moles of reactants and products, which is basically a definition of stoichiometry. It's ratios. So that means for every 1 of something it has to be multiplied by 2 or 3, or it could be the same value of 1. Just like in a recipe, if you were to look at recipes, you would see different amount of cups of something or tablespoons. It's the same thing with the balance equation. We use stoichiometry to calculate the mass of reactants, so you know exactly how much of a reactant you need. Therefore, there'll be no waste. And we use stoichiometry to calculate the mass of products we wish to obtain, to see how well we did the reaction or the experiment. Because stoichiometry is the mathematical amount. In a lab setting, we try to obtain that amount, which is pretty difficult to get 100% yield. So looking at the balance equation, what is the mole ratio between Fe2O3 and CO? It is a 1:3 ratio. You can see there's no number here, but it's assumed to be 1, and there's 3 here for CO, so it's a 1:3 ratio. That means for every mole of iron oxide you would have to have 3 moles of carbon monoxide. What is the ratio of iron oxide and carbon dioxide? It is the same. It's 1:3. That means for every mole of iron oxide I will produce 3 moles of carbon dioxide. If I had 3 moles of iron oxide, I would have 9 moles of carbon dioxide. The ratios are the same. So, in one step, the ratio of moles of reactants and products is used to convert to dimensional analysis, to convert the moles of a compound to moles of another compound. So here are some type of stoichiometry problems. Simplest one is given moles, you find moles. So it's just the ratio on the balance equation. The other two are a little more difficult because you're dealing with mass. Either start off with moles and find the mass of a substance, or you have a mass and you have to find a mass of another substance. So you can see here there's moles A to moles B. The A and B just means different compounds. In the second type, you can see moles of B go to mass of B using molar mass. And then the last problem, mass of A goes to moles of A, then moles of B to mass of B. So you can see you have a dimensional analysis of 4 types, of 4 different sections in your DA. Okay, so here's simple moles A to moles B type of problem. Using the same reaction we balanced, how many moles of iron is produced from 2.3 moles of carbon monoxide? So like any other dimensional analysis problem, you start with your given, which is 2.34 moles. Draw your line. Since it's just a moles to moles, you only need 1 cell or 2 cells. And then in the balance equation, it's 3 moles of carbon monoxide to every 2 moles of iron. You can see that from your coefficients, 3 and 2. The moles cancel out, and you're left with moles of iron of 1.56. So pretty simple. Alright, go one step further. We have moles to mole A is a mole B, but then you have to find the mass of B. So this has a 3-cell dimensional analysis. How many grams of Fe is produced from 2.34 moles of carbon dioxide? So you start back to the problem we just did, but we're not done with moles. We have to go to grams. So anytime you're dealing with mass, you always have to think molar mass. So you need the molar mass of iron, which is 55.845 grams. So notice the moles of iron cancel out. Do your math, multiply the top, divide by the bottom, you get 87.1 grams of iron. Alright, the toughest problem. You have 4 cells. Mass A to moles A, moles B to moles B, mass B. So it's going to have 4 different cells in your DA. We have how many grams of iron is produced from 45.6 grams of carbon monoxide. So in this case, our given is 45.6 grams. Now, you're like, well, I can go from grams of carbon monoxide and grams of iron. You can't do that. You have to go through moland. Moland is the central location of your stoichiometry. So you got to make sure you go to moles first. So you need the molar mass of carbon monoxide. It's 28.01 grams. Okay, grams cancel. So now you're back to moles A. So then you can use the stoichiometry of the balance equation. There's 3 moles of carbon monoxide to 2 moles of iron. Again, the coefficients from your balance equation, 3 and 2. Moles cancel, and then you need the molar mass of iron to find the grams of iron. Moles cancel. Do your math, multiply the top, divide by what's on the bottom, and you get 60.6 grams of iron. So here's some steps to solve stoichiometry. 1, you make sure you write the chemical equation. You got to balance the chemical equation. Set up your DA from your given info. And then do your stoich with your balance equation and your periodic table to find the molar mass that you need in your given problem. So here's some practice problems. Here is potassium chlorate, decomposes in potassium chloride and oxygen gas. It's already balanced. How many grams of KCl is produced if 6.89 grams of KClO3 are decomposed? Okay. So our given is 6.89 grams of potassium chlorate. Now you can't go from grams to chlorate to grams of chlorides. You gotta go through moland. So you have to make sure you convert that to moles first. So you need a molar mass of KClO3. Grams cancel. Now you have moles, so we can go from moles to moles. And in the balance equation, they are a 2-to-2 ratio. So it's a 1-to-1 ratio. Moles of KCl3 cancel out. So now we're trying to get from moles of KCl to grams using the molar mass of KCl. Moles cancel, and you should get 4.19 grams of KCl. Alright, mass percent. Mass percent is pretty simple. It's just like finding a percent of a grade. In this case, we have three elements in ethanol: carbon, hydrogen, oxygen. So the first thing is to find the molar mass of your compound. So there's 2 carbons, 6 hydrogens, and 1 oxygen to give you a total of 46.07 grams per mole. To find percent carbon, you have to take the total amount of carbon, in this case 24 grams, divide by the molar mass, and anytime you find percent, you gotta multiply by 100, and you get 52.14%, about half. So half of the mass in ethanol is coming from carbon. Do the same thing for hydrogen. You have the total amount of hydrogen, which is about 6 grams, divided by the total, times 100, and you get 13% of hydrogen. So of the mass in ethanol, 13% of it is from H. You do the same thing for oxygen. You have about 16 grams divided by the total, times 100, and you get 34.7% of oxygen. Most important thing is make sure all your percents add up to 100, because that should be your total. Alright, here we have 2 problems of practice, so you can find the mass percent of each element on copper sulfate. So copper, there's only one of them, so it's 63.5. There's only one sulfur of 32, and there's 4 oxygens around 64, giving you a total of 159.607 grams per mole. Those are the percents you should get, so make sure you can calculate those. If you have any questions in class or email. And then for number 2, you have acetylene gas, which is also called ethine. There's 2 hydrogens, 2 carbons, a total of 26 grams per mole, and you should be able to get your percents. Majority is obviously going to be carbon, because carbon weighs a lot more than hydrogen. Oop. That was the end of that. So that's the end of part 1 of 1.5. If you have any questions, let me know.